have a copy of that to show there. We have a typographic error to correct on the handout. As you'll soon discover by the change of style, these notes are actually by Tracy. No, I don't know how people in AI would write a computer program would determine which TA wrote which thing. I suppose the main way is to look at the spelling of a few words like behavior. Okay.
I use the spelling checker.
No, that's what I mean. There's British spelling and American spelling. Okay, now today I said I would talk about pictures, illustrations, trying to, especially with respect to computer science, but by popular request, people said they wanted to see my very first publication where I broke into print. Well, actually, I actually got into Reader's Digest this year, but the first one. This is from Reader's Disgust, and this is the where they have the Encyclopedia Britannica on pages 144 and 43. But no, on the front cover of this was this was my first, and I was co-author with Ernie Kovacs, and anybody ever hear of him? This was 1957. And let's see, Science Department, page 36. Here we go. So now this, and I got $25 for this article. $25. Yes, I became rich immediately. So this was it. And I sent them just a mimeographed. I gave them a mimeographed handout just for the heck of it, because I had based the system of weights and measures on things from Mad Magazine. I had no idea of publication, and I believe this joke here was actually ripped off from Roger Price. Anyway, but it was wonderful illustrations. Since we're talking about pictures today, we had probably the best, up until the tech book, it was the best illustrated thing I ever wrote. And it's a very logical system. It's all based on, you see, here's the units of length, and the for Schimmelpotter ZB is the very small one. You got volume, mass, everything in there. In fact, time was also decimal. This was the main innovation. That instead of having a 365-day year, we had a 100-day year. It makes it much easier for calculations, and your birthday comes more often. So, this was something that they completely changed, because I had named the units of time after the editors of Mad Magazine, the original Mad Magazine, Harvey Kurtzman and his gang. But they had all recently left and founded a new magazine called Humbug, and so all the new editors were named, got named units of time named after them. We started with October 1, 1952, which was when the time system goes, and so on. And then since everything was so logical, everything was very decimal, so I also I felt there was a need for something else, and so I introduced the unit of counting. Oh well, that was my first excursion. On my Vita, yes. This is number 1 on my Vita. I also used it on my. I ran for student government, and I lost miserably. But I used this as part of my campaign, but it didn't help. Okay.
So does writing for Mad pay better than writing technical articles?
Yes, I think the next time I got any money was about 15 years later. There was the ACM computing surveys used to pay $500 to authors for expository articles, and so that was about 1970 when I first had another nickel from writing technical articles. On the other hand, book publishing, that's feast or famine, but it's But a book like The Art of Computer Programming, it's more than my Stanford salary. So that that was that became a problem as to what charities to support and so on. But so there's $25 here. I think it was worth a little more in 1957, but not that. Yeah. Okay, now my second article was the one I was really going to show you. This was in the Communications of the ACM. It's about Runcible. What was it? Revised Unified New Compiler, Ingenious Basic Language Encoder, or something like this. We had to find some reason for every acronym in those days. Pascal was just named after Pascal, and so I wanted to show you this because it's. I think it has the most complicated flowchart in the world. This is spaghetti, an example of. But I decided to present the entire algorithm in this chart. So it doesn't quite succeed, I don't think. I mean, although it's all there really, and I could we would do it quite differently nowadays. Yeah, this is here it goes. In fact, I corrected an error here. This should really go up there. I don't know, but that's in my own copy. Still, the way that I explained the algorithm was something that I still believe is about as good as I could do, and that is this play-by-play account. And so I give an example that's somewhere in here. Here is the kind of programming languages we had in those days. This was on a machine that had 2,000 words of memory. That's decimal 10-digit words, so that's about 4K bytes of memory, and we couldn't have done it in 1,999, but 2,000 was just enough, so we didn't have identifiers. Everything was subscripted, and so you had I variables, C variables, and Y variables. I's were integers, and C's and Y's were floating point. And then you could have constants and parentheses and stuff like that. But we didn't go into a lot of parsing. And I used this example because a previous article had come out with this example used as to how it would go, except I added another minus sign here because this was to show something more in the algorithm. So now anyway, so then symbol scan 2 C. This is a bottom-up parsing algorithm. We didn't know what it was at the time, but this is but the main idea is that there's you can play through the flowchart and follow it by the symbol comes in, you start at start, and symbol comes in, and then it tells you can see here whether you got through the loop okay, and then once in a while it would go and add some machine language to the program, and I defined the machine language here and the final code. So but the main thing I want to show you here was this flowchart, which is something I've overcome since those days. Another thing I had to overcome, I didn't when I published this paper, I was a junior, I guess, in college, and I had just read this article that came out in the June issue, and I said, hey, we know how to do it better than those guys did in the article they'd published, and they were professors. And so, but we didn't think about that so much. We just thought we had a neat idea that we would want to explain to other people. So I wrote this up on behalf of the computing laboratory where I was working part time. But it didn't occur to me to mention any of the other people's names who were really responsible for most of this. I was just it didn't occur to me that I was going to be getting credit for these ideas by publishing them. That was a completely new concept to me at the time. And so the algorithms that are described here were really due to largely to a friend of mine, Bill Lynch, and the flowchart was drawn by another friend of mine, and so on. So all I did was do the writing, and I thought that a year later, I learned a little bit more about what's kosher and so on. And so when I actually refer to this article in The Art of Computer Programming someday, I have to make it clear that who gets credit for it. And meanwhile, I've written a bunch of letters and so on. But I did make that mistake too. And many young authors have done this. In their early papers. I should have have these other people as co-authors, or certainly had big plain acknowledgments to saying what it is. Yeah. And so several other young people have done this too when they published their first article. In other words, they're so interested in publishing it, in getting the news out, that it doesn't occur to them that there's also people giving credit to authorship, which is I mean, some people only write papers because of the credit, but other people do it without thinking about that. And this has and so then those of us who made this mistake tend to go overboard afterwards. And for a while, I had many co-authors. Did I tell you about the time Paul Erdős had the porter in the railroad car as a co-author? This is one of the But you had a question? No. Well.
I was just going to comment. I think another common mistake is to not make your bibliographies complete.
I didn't have a referee report on this, that's for sure. This came out in November, and I must have written it during the thing. Now, the bibliography was just the only things that there wasn't very much on. In fact, this was sort of the first article about how to do parsing that had come out. So at that time there wasn't much to say. But yeah, you're right. I don't have a single bibliographic item in that article in MAD, for example. Let's see. What did I bring this for? Oh, yeah. Now, flowcharts aren't completely obsolete. There's still some value to them, and I wanted to, especially if they're small. And I guess people know, for example, the syntax diagrams in Pascal manuals or something. In the appendix, there will be little charts that will tell you what the Pascal language is. Those charts tend to be useful. Here's the first example of such a chart, and it was actually a larger thing than the flowchart that I published, but still indexed well enough that it's possible. Yeah, this was Algol 60. Or slightly extended Algol 60, but it actually people would hang this on their wall, and they would use it like people use a chemical sequence, a periodic chart for chemistry. And this was the origin of this kind of ideas. And so you had, here's your favorite, my. Let's see, where's my finger? Oh, here, yes, okay. Dummy statement, go-to statement. You see right there in Algol 60, go-to, followed by a designational expression. Algol 60 allowed you to go to an expression where you could then find designational expression in M19 on the chart. And so here's 19, and M is down here, designational expression. Here we go, designational expression. And so it's a simple designational expression, or which is a label, or a switch designator. There were such things as switches, old obsolete features of programming languages. Parenthesized designational expression. Okay, but anyway, you get the idea, I think, from this chart pretty well what this language is. Probably better than reading it in syntax form. So that's something about charts. Still, you're working on finite state machines. The book that I'm writing now, we have a little example of the states that you can be in when you're waiting to get two heads in a row. So one state is you haven't seen any heads yet, and another state is you've seen one head, and the third state is bingo, you've got it. And it's a nice little state transition diagram. So nothing wrong with little flowcharts like that. Okay. Now, the article, the Programming Pearls article that I showed you about literate programming, was actually a two-part article. The first part was the part I gave you in the handout, which was a small example, and then the second part was my solution to John Bentley's challenge problem that he I said, I really believe this is the way to write programs, and the only way is for me not to send you a program on a topic of my choice, but for you to choose the topic and me write the program for it. And then when he published that was in the following month, probably June of last year. He published it together with a review. He figured if this is literate programming, there ought to be literary reviews as well. And so here he went and asked Doug McElroy to go and write a literary critique of the literate program, and what would Doug say. And a point that I'm not sure if this is Doug's idea or John's, but anyway, John found that one thing my second program was missing was a picture, which would have explained things that I decided to describe in words. I was describing a data structure which is fairly new to I mean, it was something in Frank Lang's thesis that I was trying to promote in this program, and so I described it in words, but I didn't have a diagram. And so John said, wouldn't this be nice to have a diagram in there too? And there's no reason why I couldn't. I mean, in web, you can use anything in tech, and tech it's not hard at all to make a diagram like this. I mean, he said it took. If you know a little bit about tech, what's this laughing going on here in the peanut gallery? We got arrows in LaTeX fonts. The arrowheads aren't too bad. But this would, now John said here, I typeset this picture in an hour or two using the PIC language. We could have used tech features to include such a feature in his web program. And certainly I could have done that. And also in that big book I showed you, the tech program itself, I taught a course out of that book last spring. And as I was giving lectures and I was describing the data structures in the lectures, I started drawing diagrams on my pad, and the students said, "Hey, it would have been nice to have those same diagrams in the book, wouldn't it?" Yeah, I agree. It didn't seem to me at the time, though. At the time, I was thinking only algebraically. I was thinking the way to get into data structure is to know what the macros are that you need to dig into it. But that's because I already knew the data structure. If I was learning the data structure for the first time, the diagrams would have helped make that sink in. I forgot to tell you the punchline on Monday. I showed you this diagram that I was proud of in the typesetting program that showed the two things coming together, and when they overlapped, you had a page fault. But I failed to show you one of the referee's comments. Said the figure was too detailed. Okay. Well, I just figured. Heck with it. I don't think it's too detailed, but for him it was too detailed. Now my own attitude is it was something that you could look for the detail if you wanted to, and you could find it if you didn't want it. You didn't have to. But I really believe in having something that you can stare at if you want to for further information and to get the idea. I don't think I could have gotten across a real example, the reality of it, with a less detailed example. On the other hand, I tend to be a person who prefers minutiae. I guess you already know this. My lectures in this course tend to talk about small points rather than the overall picture. Probably our guest lectures will give you more of the overall flow, or I'll try to think of the overall. But I tend to be concerned with little details most of my life. I mean, I even got to the point where I started designing the ABCs at the end there. So I tend to work on small details more. Anyway, here's the thing though. Pictures of data structures seem to help some people, and I guess especially in this kind of a data structure, it was valuable because it was a novel concept. Okay, now another paper that I wrote with regard to tech was about the way that tech breaks paragraphs into lines. This is the most interesting algorithm inside of tech, and I wanted to present the algorithm, and so it's not a trivial algorithm, but I wanted to present it with all its bells and whistles in a publication. So this is a paper that I wrote with Michael Plass, who also did his thesis in generalizing the paragraph making to page making and placing of figures and things like that. And so we did this paper where we surveyed what had gone on. And by the way, you talked about bibliography. Here we had a pretty good bibliography in this one. In fact, it includes quotes from Bernard Shaw saying what he thought about the printers that printed his works as far as breaking lines is concerned and things like that. So this was researched. This was researched pretty well. We used examples of fine printing where this had been done, where you could also look at the printing was complicated enough that you could look at it and figure out sort of what the guys were doing, even though they didn't explain what they were doing. So that's part of it. Okay, but now the main thing was how to describe the general problem and how to describe the algorithm, and so first we describe a data structure for the input. So we have to describe some kind of test data, and so here I have a description of the test data with all the parameters here, which describes, and it's some test data 601 things long, but the main idea you can get, we have a paragraph here which we're going to be looking at. We're going to be trying to typeset, break it into lines. It comes from Grimm's Fairy Tales. Happens to be one of the things we have online at Sale. We have if you want text to use as examples, we have Harold and Maude, and we have Wuthering Heights, and we have this Grimm's Fairy Tales. Okay, so now this was the first paragraph of Grimm's first fairy tale, and we use this for an example. And the example the thing that's shown in here, the little triangles show where hyphens are possible, according to our data. So we're giving this, this is the test data. Assume that we've specified all permissible places for hyphenation, and so now it becomes a problem of finding the best way to break this paragraph into lines. There's little numbers at the right here too that show how tight the lines are. Like a minus means that the line is compressed more than it. The spaces between words are a little tighter than usual. A plus sign. These are fine print, but a plus sign means that they've been stretched a little bit. And so you have a plus 965. That means that it's stretched. This line here, cool fountain, is pretty wide. The previous line is minus 0.896, is pretty tight. All right. I think we showed. Where did we show in the? Oh yeah, here was something that we had fun getting the typesetter to do. Our main goal was to find a way to avoid choosing any breakpoints that lead to lines in which the words are spaced very far apart, or in which they are very close together, because such lines are distracting and hard to read. They had to, we had to communicate to the printers in England about this at some length. But this was okay. Now so then we describe the input data, which it starts out with an empty box at the beginning for the indentation, then the letter I, the letter N, inner word space, and all this goes on. So we describe the data. Then we give examples of how it's done by brand X. This is called the first fit method, which is the way people usually go about and break paragraph into line. Brand X says you get to the end of a line, and then you're at the end of a line by a certain criterion. The next word doesn't fit, and then you stretch it out essentially, or you find the best of the two possibilities if you have two. There is hyphenation too. That's I think they would get in as much as they can. I think the first fit method packs it as tight as possible, including hyphenation. And then there's the best fit method, which uses some scoring, and this did a little different. It comes out with a better score. That is, you can compare the paragraphs, and you get and it comes out better than the other one. It allows some judgment. Doesn't pack it as tight, but we'll loosen it up if that seems to, if that's better in some what do you call it, some way of scoring it for goodness. And now then the optimal algorithm I describe here has something where if you look at all these numbers, there are fewer glitches and it all turn out to be better. And so now I have these desirability criteria, which are called demerits that are charged to each line. And when you look at the figure and you get numerical scores, and you can see the big ones, and you see this first fit method had that real stretched out line there that got 8,000 demerits, while the best fit did all right on that one, but it had some other, but the optimum fit was able to avoid all the bad ones after the beginning, although they started out all three the same. And then at a different width of line, we had another thing. Now the idea of the optimum fit method is you go through and minimize the total number of demerits. You have an algorithm that just finds the absolute minimum number of demerits over all possible ways to break that. And it's possible to do this. And the next thing I did was show somewhere in the paper I thought I showed it. Maybe I missed it. Excuse me a minute. Time out for commercial. That's the main illustration I wanted to show you. Don't tell me I left it out of the paper. Maybe. Oh, yeah, I see. Because actually I was explaining the algorithm in detail later on in the paper. So here's the picture that shows now this particular algorithm. This is the way what I wanted to get at. How are we going to describe the optimum fit algorithm? And a diagram was a reasonable way to do it. Here, you start here at this dot, and then if you had two ways that were reasonable to break the first line, either after the word A or after the word king. I have another example here on the facing page, so you can read this. But anyway, so you could either put break it here as we did, or after the word king. There's a little line in here which shows a permissible. Well, that's another thing. But the main idea was that if you broke after king, you would pay 1734 demerits. At break-in after A, you paid 2357 demerits, and so the best fit algorithm would choose king. It was a better way to do the first line. Now then, similarly, after A, then if you broke there, then the second line could break at the end after was. If you broke after king, you had only one reasonable place after so. And so then you'd have to, so the best fit algorithm loses right away because it makes a good greedy first choice, but then it's stuck, and the second line has to be bad. While if you held off and made the first line a little bit worse, you could do real good on the second line. So this makes a little picture of the possible ways, and the main idea is to find the shortest path from the beginning down to the end of the paragraph here. At the end of the paragraph, there's lots of things that you can do because the last line is filled at the right, so things don't get very bad on the last line. So anyway, so Tech has a way of essentially finding the shortest path in this maze. And then this illustration here showed the paragraph for the data, but it also put little lines in showing. Suppose you increase the tolerance, and you said Tech cuts off and says that I'm not going to look at anything with more than so many demerits, and anything more than that, I'm just going to assume we're going to be able to get away without going that way. And then so Tech doesn't even consider all those possibilities. But in this one, there's little lines showing the extra possibilities you would do if you increase this tolerance and told Tech to look at a much larger maze and try to find the optimum in that. It would take longer to run, but you would be guaranteed to be able to handle some really bad cases, which might come up once in every 1,000 times. So that's the way I presented the algorithm. Besides how we gave, people also play with things. So we gave many examples here. Here we gave some examples of what you'd do if you asked it to set it with take extra long. Make it 3 lines longer than it should be, because you really need somehow. This looks so terrible. I don't see if anybody would actually do it, but the algorithm is prepared to do that if you ask it to stretch out. Okay, so then we have to present the algorithm, and so we do that in the way that you're by now familiar with a web-like style. This is before I capitalized names of subsections, so it looks funny to me now. And then we also describe a computational experience. We give a chart like this showing the in the entire volume 2. How did it do in this book? How often did you get? This is a histogram showing how often you, like 0 here means that the spaces were just at the right at the normal. Right, this line here is sort of a line that was set without compressing or shrinking the spaces, and these lines are very tight up at the top. These lines are stretched out at the bottom, and so it. Then I comment that this data is biased because if I had a paragraph that really looked bad, I probably rewrote it, and so in order to get more true data, I took part of the book and I retypeset it with a different line width, and then I got spaces like this compared to comparing the optimum fit to the other typical method that people use. Okay. Anyway, this was the way the algorithm performance was then demonstrated by charts. And then I have examples from Bibles where they had to typeset the Latin corresponding with the Hebrew with the same thing, and it's funny that this old Bible here they felt it was so important to have lines the same width that they filled in a whole bunch of O's in here. But anyway, we could look at a lot of examples from old printing and find out how new methods compared and so on and so on. Okay. Now there was a book that came out talking about how to present charts, and had very good reviews. This came out about 2 years ago, and it doesn't solve all the world's problems, but it gets you thinking about the problem of making good charts. And so if you have a problem with this, I would recommend that you look at this book and get to thinking about it. And the main thing that he doesn't like is pie charts. He thinks that they're completely hopeless. But he gives many examples of things from some recent, some otherwise. I guess the best source now is USA Today, isn't it, for charts? Here's one from Russia. Tell from the style. 1980 plan. Okay. Well, there's a book called How to Lie with Statistics too that you ought to look at. It's hilarious. It's by Darrell Huff. He wrote it. He shows how to get people thinking that the data is different from what it is. Like one of the ones I remember is how he takes sacks of flour. He's trying to show something like a sack of flour that's 6 inches high and another one that's 7 inches high. Something has gone up from 6 to 7. Well, when you see the sack of flour that's 7 inches high, it's a three-dimensional object, and so it's really the ratio is 7 cubed to 6 cubed, which is much bigger than the ratio of 7 to 6, while the data was actually talking about a number that went from 7 to 6. And so when you make these charts, you can also confuse the issue. See, so what were some of the neat things that he had in here was scatter. He was able to put words in among the data points. In a way that was reasonable, that was kind of interesting for the so that you not only have a graph, but you have other things to read here. The length of an organism at the time of reproduction related to the generation time, so he has some ideas for that people tried, some that worked, some that didn't work. Here's a funny idea that people have to put it into faces. Have you seen this one? Let me see if I can find them. Do they have faces here? Anyway, we're supposedly wired to be able to pick out features of faces in certain ways, and so they thought they would present the data that way. Let's see, faces. Nope, it doesn't have it under faces. Friendly data graphics. What's that? Friendly data graphics versus unfriendly. Words are spelled out, mysterious and elaborate encoding avoided, unfriendly, abbreviations abound. Friendly, words run from left to right. Unfriendly, words run vertically, and so on. That's his idea. Okay, and then he has comment from Joseph Albers, who's the guy who's famous for the Albers wall outside the physics tank here, and so on. He's one of the big teachers of graphic design. I think he was, yeah. Okay, so here was, this looks like a chart that you see, this is New York Times, but this is some good examples where you can combine syntax with semantics. You can see the picture, and you can also look at it further if you want to get the detail. So that was so some good ideas in here. What? The faces? Oh yeah, Tracy will look for the faces while I'm showing you Terry Winograd's book. Terry's book, Language as a Cognitive Process, had difficult things to describe. He's talking about parsing algorithms for English language here, for natural languages, and so he's got some little charts and so on. But the main thing that let's see if and then he has his data structures are described by little frames or whatever you call them, and he has these pictures in here. But let's see if I got to find the way that he gives the nested structure, which has to. He had to. Okay, he's got things like this, which shows the way things map inside of others. So he's got. But that's still data structure. I got to show the algorithm here. He's got a recursive transition networks. Let me see. Where do we have some of the norm? Okay. Well, this is. I think just by paging through here, you can see the idea of how he has got his algorithms described by giving a lot of structured examples of how they work. Let me see now. But I'm still trying to look for the kinds of things where he's actually got this. Maybe it's later on in the book. See, here he's got diagrams of sentences, but that's not what I wanted there. Maybe it's all on one page, and I was the page that I should have looked it up before class. He's got play-by-plays in this, to describe the algorithm here. But I remember he wrote a bunch of computer programs that were able to do this indentation. He did this with the very first version of TeX. He broke it all the time. I added some kind of macros just for him. This is a grammar that he has here with you see, this is what Tufte calls not user-friendly because it's going up and going vertically. I don't know what Tufte would do. I think the book was Okay, so I guess this is the kind of thing that I'm thinking of here, where it's just the way he's got the algorithm described hierarchically in these parts, and that seems to work because he's describing a hierarchical thing, and he could do it instead of a tree diagram. You could do it with boxes inside of boxes inside of boxes, and get the idea. Yeah, here's his way of describing algorithms. Okay, so it's like that. Okay, so did you find any faces?
3 places with faces.
Oh, okay, so let's see what.
I don't think the first one's in there.
Half faces carry the same information as full faces. They might be easier. Okay, now let's do. No, somehow I don't see doing that in my. Oh, this is pretty neat. Cartoon faces. Okay, this is actually Herman Chernoff's idea. He was a Stanford. Herman Chernoff was a great loss to Stanford when he went east. Okay, so yeah. Oh goodness, here's the normal law of error stands out in the experience of mankind. Here we go. Oh well. And Tracy found another one. She looked this. This was interesting. This is a different kind of. This isn't to display data, but this is to show the places of where skin cancer occurred on a man's head and Hals, his throat, and so showing it on a man's face, obviously a win with a person's face. And these are supposedly you can learn to understand these. I have to get interested in the problem to know if it works or not. Okay. Now let's see. In my own book, I think the most complicated thing I had to get across was an elevator. This is an example of a what do you call it, multitasking or parallel environment where a lot of things are going on at once. I'm simulating the elevator system at Caltech Math Building. Tracy will remember that elevator. I rode up and down that elevator with the stopwatch, taking notes, calling to people. Now push the button on the 3rd floor, and we'll see what it does next. Elevator system 280. Okay, and so here I was describing a bunch of coroutines, one for the people, one for the elevator, and then I got the description here to show, which I think people have read this through. I mean, this is about the only way I could think of to explain what's happening, but it's not diagrammatic, and so it would be interesting exercise for me to see somebody go through and some graphic designer to go through it and see if they could figure out a way to present this better. But I still, at least I could describe where I what the time is on the clock and what state the elevator is in, what floor it's at, and whether the doors are open, and what step we're executing, and then there's different coroutines going on, and seeing something this way, best I could think of in 1960s. In the 3rd volume, I've got a fold-out illustration, which was great fun, especially to see how this comes out in many other languages. When they translate the book into other languages, I always turn first to the fold-out and see how they did it. I think this was okay. Now this took me several weeks to draw it, so I should be able to find it if I look hard enough. It's in this part. Actually, here we go. So we got a diagram like this. Now this one, I think, does convey something that you could only otherwise do by sitting and watching tape units winding back and forth. It's talking about how to sort numbers on tapes. And I discovered as I was writing this book that most of the people who wrote papers about how to sort on tapes had never seen the process actually gone. They were playing some mathematical game, but they didn't realize it took time to rewind the tapes and that there was certain overlaps and buffering and things going on. They had these neat algorithms, but when you actually saw what happened, it didn't work that way. So I wanted to give the feeling of reality. So if you look at this tape here, there's a code which indicates, like this hash mark here means I'm reading the data. So off of the 6th tape, I'm reading it, and a black mark means I'm writing it. And so I read some data and I fill my memory and I write out. This is a lot of data. So this is one memory load full of data, and then I distribute. And this was Brand X algorithm. This is the one that everybody started with and wanted to. We're improving on by their other algorithms. And you go 1, 2, 3, 1, 2, 3, 1, 2, 3 until you get to the end here. Then you rewind everything. These dots mean now you can see the tapes whizzing backwards, rewinding. And then you start reading from those 3 tapes, 1, 2, and 3, and they write onto tapes. By this time you know how many records there are. They write a certain number onto tape 4, and then rewind tape 4. Then they start writing on tape 5. This circles here mean the operator has to go over to the tape and dismount it and put a scratch tape on, because it was the input tape. You don't want to destroy that, and so you have to wait for that. These practical considerations take place in this thing. So you're reading the data, merging things onto and the strings, the little white dots tell how long before you have a break. This means it's ascending. You can actually get things that are longer than your memory size in ascending order on these tapes. And then the 3rd tape gets it. By this time it's all rewound and got a new tape mounted, and you can rewind it. Then we can read from tapes 4, 5, and 6 and merge onto tape 1, 2, 3, and then we rewind again a little bit and so on. And finally we get the answer, and here we are, and that is done in a little less than 18 minutes. Okay, now we take the improved algorithm, the polyphase merge, which was for 6 tapes, was considered to be a big improvement. Well, it turns out that the polyphase merge was waiting a long time for rewinds, when there was nothing possible to do, because you had to rewind a fairly long tape. And so if you check it out, even though it was it was supposed to be a win according to the calculations in the paper in the journals, it actually took 18.5 minutes to do that. While it was supposed to be quite a bit faster than the other ones because of the rewind time. And not being able to see a chart like this, you wouldn't get to see where the bottleneck was. There's another algorithm that's one of the first algorithms to be patented, and it meant that nobody could actually use it without paying a royalty on it. And this one was, they thought it was so good they would patent it, and that's the one at the bottom here. I'm pleased to say that one was the big loser of all. And then by actually looking at this data, we're able to come up with some algorithms that avoided the wastage of the time. But this kind of a chart. Now, it took me a long time to prepare the chart, and it took Addison Wesley. They had to farm it out to another studio. Their regular artists, said, "No, I'm not going to do this," and so they had somebody else do it professionally. Now I would typeset it, of course. It wouldn't take me as long. I would get it more accurate. I would have a computer program generate it, and it would be so. Oh well. So every problem seems to. There's a few general themes that we kept coming back to here. Play-by-plays, but each algorithm has its own domain that's going to probably make you interesting for every paper you write. That if you want to figure out the best way to do it, you can only get You can get ideas, and you get your mind off of the old ways of doing it by reading a book like this, by seeing other papers. But I don't have a general recipe for how to do the optimum figures. Okay.